My date, apparently he's a polygamist.
Well, it's Friday night at Cary. Welcome back. You can tell by the buzz in the room that many old friends are seeing each other tonight. And tonight, of course, we have a real treat to honor and listen to one of our own, that being Gene Likens. Gene is retiring after 29 years at the Cary Institute at the end of June. And we thought some kind of event to allow Gene to talk about his scientific career here and elsewhere might be a really appropriate way to mark that occasion. He, of course, founded this place in 1983 and built it with a wonderful staff in science and administration and operations that has allowed it to have the international reputation that it enjoys today and that we hope to be able to continue on into the future. I must admit it was when I was hired in 2007, not only was it a great honor to be the second president here, but I also realized that was going to be an enormous set of shoes to fill in this organization. Of course, working with Herb Borman, Gene made the Hubbard Brook ecosystem a landmark of how to do ecosystem science. It's in every textbook. Even my high school biology teacher, when I went to Dartmouth, told me the first thing you got to do is go up and meet this professor, Gene Likens, who's there, and he's got this ecosystem project going, and it's going to be the hottest thing around. And so as a freshman, I staggered on up to Gene's office, made that acquaintance, and here we are tonight. Hubbard Brook is in every textbook across the country and around the world, and Gene's work at Hubbard Brook and here certainly led to the discovery and elucidation of the whole acid rain phenomenon, what caused acid rain, what we would have to do about it. I think it's not unfair to say that a lot of his work led to the implementation of the Clean Air Act that's had a substantial success story in improving our atmosphere, cleaning up our atmosphere. Now, I have heard Gene say that when he was growing up, what he really wanted to do was play baseball. And along the way, I found out that he earned a spot in the Basketball Hall of Fame at Cited County, Indiana. Sure, I butchered that pronunciation. But his work in ecosystem science is certainly his lasting legacy. Beyond his PhD from the University of Wisconsin, he has no fewer than 9 honorary degrees. He's a member of the National, have I missed one? We're up to 10 now. Okay. He's a member of the National Academy of Sciences. He upstages original fighting. And with Herb Borman, a winner of the Tyler Prize and the Blue Planet Prize for international recognition of the importance of the work of ecology. I think most significantly, he's also the recipient of the National Medal of Science from the President of the United States in 2001. So tonight the floor is his to reflect on his years at the Cary Institute, his career of work, basically to get the acid out of our atmosphere. Gene Likens.
Thank you. I can't really say it's a pleasure to be here because I've been here for a long time. But to see a couple grandchildren in the back waving at me, that's pretty special. Phyllis and I came here in July 1983 to found the Institute of Ecosystem Studies. I stepped down as president in 2007, and I'll officially retire on the 1st of July. I'm very proud of what we, and it certainly has been a partnership, have accomplished. In the short time of a decade or so, our tiny scientific institution built an international reputation. When we were introduced as speakers and colleagues around the world, it wasn't then any longer necessary to say where the institute was or what it was. This is probably the best academic job I've ever had, but that's another story. I will continue to do science as long as my brain works, and it is one of the major passions in my life. I've been extremely fortunate in science. It's been stated that most scientists are fortunate if they have one really important discovery in their entire career. I was fortunate to have two, but I'm only going to talk about one tonight. I joined the faculty of Dartmouth College in 1961 as my first academic job, there with three colleagues shown here on the screen. Initiated the Hubbard Brook ecosystem study in 1963. I'm fond of saying that I was 15 then. Our goal was to diagnose the workings of complicated forest and aquatic ecosystems, entire watersheds, by measuring the chemistry of precipitation, the inputs, and the chemistry of stream water, the outputs, much like a physician would measure the chemistry of blood or urine to diagnose the health of a patient. That was our approach, to diagnose the health of a watershed. Our first major discovery turned out to be extremely interesting and important, and has kept me quite busy for the past 50 years. This is the story that I want to tell tonight. Acid rain is really a very simple phenomenon. Through the combustion of fossil fuels, coal and oil primarily, sulfur dioxide and nitrogen oxides are emitted to the atmosphere where they're converted to really strong acids, sulfuric acid and nitric acid, two of our strongest acids. And then those acids come back to the land and water surface through rain, snow, sleet, hail, whatever, and in dry particles and in gases. So it's really what acid rain is. The very first sample we collected at Hubbard Brook in the White Mountains of New Hampshire, the 24th of July, 1963, that summer, had a pH of 3.7. We were stunned because that is about 100 times more acidic than we had expected that it should be. Of course, we didn't really know what it should be, but we didn't expect it to be that acid. We continued to measure all storms of rain and snow that first year, and the volume-weighted average pH turned out to be 4.12, also very acid. So we wondered, where was acidity coming from? What was the cause? What had it been like before? How did it get that way? All the fundamental questions as a scientist you have to try to answer in order to understand a situation like this. So that's what we attempted to do. And it wasn't until I changed jobs, moving from Dartmouth to Cornell in 1969, I set up precipitation collection systems around the Finger Lakes here in central New York, and discovered that the pH of the precipitation was just about the same as had been out here in New Hampshire at Hubbard Brook. In other words, these are just about the same. And that was another surprise and a shock that they should be the same. That was our first clue that this problem might be something more regional, and not something peculiar to the Hubbard Brook. We wondered if the acidity of rain at Hubbard Brook could be in any way related to the granitic nature of the White Mountains. Well, that one didn't make a lot of sense, but we didn't have a lot of answers. So this was our first clue that it might be a regional problem. We prepared these results for publication and published them in the journal Science in June the 14th, Flag Day, 1974. The article about this finding was carried on the front page of the New York Times the day before, the 13th of June. That article on the front page of the New York Times changed my life forever. I received phone calls, there were no emails then, I received phone calls and letters from all over the world saying, what is this stuff? What are you finding? What you can't read on that page, I know you can't read it intentionally. This is what it says in summary. It says that the fact that the chimneys and smokestacks were greatly increased in height in the 1950s and 1960s changed what I call a local soot problem to a regional air pollution acid rain problem. It belched it out much higher into the atmosphere so that it could spread over a much larger area. But the 1970 Clean Air Act was focused on removing particles from the smokestacks. Some of you might remember that it was actually kind of tough to breathe in places like Bethlehem, Pennsylvania, or Pittsburgh, or Fort Wayne, where actually if you hung out your laundry, it often came back in dirtier than before you washed it because of all the particles that were in the atmosphere. So the 1970 Clean Air Act amendment was focused on removing those particles. We argued in this paper that those particles affected some of the acidity by neutralizing it. And by removing those particles, allowed more acidity to belch out the smokestack and therefore to be spread over a large region. That was a very controversial idea at that time. We also argued that this was really an ecosystem problem, and it could not be addressed in a piecemeal basis, that it was a complicated, integrated problem that required an ecosystem approach. There were preliminary indications that it might affect forest growth. I'll come back to that later. And as I say here, a portent for calcium leaching, which was a major finding later on, not in 1974. So that paper was an interesting paper, I think. It gave the regional dimensions, but the fact that it came on the front page of the New York Times gave it an elevation that the science itself would not have. So this is going to be a part of the very important part of the story that I'm telling tonight, the interaction between science and the media. It seems to me that environmental problems often have a trajectory very much like I've just described for acid rain. A problem is identified. I'm plotting awareness here or response or whatever you like. The problem is identified usually by scientists, often by environmental scientists if they are environmental problems. And it goes along with very low awareness until it's discovered by the news media. And then the awareness shoots up like a rocket, and fingers start being pointed. Aha, you did it. No, you didn't. I didn't do it. You did it. And you go through this long reaction of, yes, you did. No, you didn't. Yes, you did. No, you didn't. You're familiar with this with almost any environmental problem you want to think about. you're wrong, the data are wrong, the vested interest, whatever, is arguing, yes, you did, no, you didn't. And that goes on. I don't have a time on this axis, although it's moving along in this way. It might be years, and I'm going to come back to that point. But you go along until something happens. If there's a scientific breakthrough that says, oh, that's the way it is, yes, you did do it, and the problem is resolved. Unfortunately, that doesn't happen too often in my analysis of looking at these kinds of problems. Sometimes politically, it's better to get on with it and resolve it, and that's what happened with acid rain, and I'm going to come back to that. Sometimes there's an economic advantage. That was the case with solving stratospheric ozone, the release of chlorofluorocarbons and the destruction of stratospheric ozone. The company producing most of those chlorofluorocarbons had another product ready to go onto the market. So they finally decided, oh yes, we need to deal with this problem. And by the way, we just happen to have your remedy to this problem. But most often what happens is boredom. We, the public, just get tired of hearing about the issue and it goes away. Maybe never getting resolved. And at any rate, this process often takes a very long time. So you can think about this in terms of DET. Rachel Carson, here's Rachel Carson, here's her book, Silent Spring. You can think about it for any number of environmental issues. So most of the emissions from the combustion of fossil fuels, coal and oil, occurs in the Midwestern United States in the production of electricity. About 70% occurs in the production of sulfur dioxide emissions occur in the Midwestern United States. The winds tend to move from west to east. They're much more complicated than that. We've done very detailed analyses of that. But for general purposes, they tend to blow from west to east, you know that. And so these pollutants are carried from where they're generated, from these high stacks, to us here in the northeast and the southeastern part of Canada, and dumped on us in rain, snow, sleet, hail. So the garbage is released here and is dumped on our lakes and forests and streams here. That's exactly where it is. If you guys would like to come down and sit, please do. The seats are more comfortable with the steps. So essentially that's where the emissions go. This is one of, if not the tallest smokestack in the world. This is in Sudbury, Ontario, and this stack is 380 meters tall, 1,250 feet roughly tall. In the smelting of copper nickel, huge amounts of sulfur were released. When this was in full operations, more sulfur was emitted from this single stack than all of the active volcanoes in the world each year. Huge amounts of sulfur were emitted from the stack. Now you see the plume. Sometimes it came toward the United States, but most of the time it stayed within Canada. But there was an issue brewing, because the Canadians were arguing that they were receiving more than half, therefore the majority, of their sulfur in the atmosphere from us, from the United States. And they didn't like it one bit. So we were dumping our garbage on them. So during the Carter administration, President Carter started a memorandum of intent with the Canadians to try to resolve this transboundary problem, to try to reduce the emissions, and you can't control where they're going to go through the atmosphere, but to try to reduce the emissions. So this had proceeded along quite well, and then some of you will remember the Iranian hostage situation. that effectively did President Carter in. Maybe a lot of other things did as well, but that finished him, and so he was not reelected, and President Reagan, Ronald Reagan, was. And one of the first things that President Reagan did was to literally shelve these documents, were feet long, many, many feet long of documents ready for the agreement on the memorandum of intent. And with Prime Minister Mulroney, it didn't go anywhere. So President Carter's proposed memorandum of intent between the U.S. and Canada was discarded. That led in many ways to what I call the acid rain wars of the 1980s. One of the EPA employees, an assistant administrator for air, noise, and radiation, Kathleen Bennett, said this: "Within 2 or 3 years, we expect to have some very important findings that will help guide us. It is possible that those will suggest further activities that are necessary, and it is possible that they won't." Unquote. Unbelievable. Unbelievable. In September of 1983, I had just come here to the Institute of Ecosystem Studies as the new director. I led a small team to brief President Reagan and the full cabinet on the issue of acid rain. We had a full hour with the president and the cabinet, which was unusual. I think it was the first time that that had occurred, certainly on an environmental matter. We presented the case that reductions in sulfur emissions were needed, and we gave the amount that we thought were adequate reductions to help ameliorate the problem of acid rain. Seated to my right is William Ruckelshaus, who was the administrator of EPA at the time. Some of you might remember that President Reagan had a great fondness for jelly beans, and he often, probably almost always, I didn't go that many of his meetings, had them in an apothecary jar on the table, and there they are. So he invited us, there were 4 of us, he invited us to have a jelly bean. And when they came to me, I reached in and grabbed a whole handful of jelly beans, and I put them into my pocket like that. They made wonderful gifts. My mother, who's now 103 and a half, thinks it's the greatest gift she ever got from me. A jelly bean from President Reagan. At the end of the hour of our briefing, President Reagan sat back in his chair, that chair that he's in right there, and he said, "Well, gentlemen," this is a direct quote I'll never forget, "Well, gentlemen," and you can look around the room, "Well, gentlemen, it's clear to me that my undergraduate education did not prepare me for such complicated issues," unquote. I thought, good grief. Wonder where we went to undergraduate school. I didn't know at that time. And I thought, given all the problems that a president has, it's a remarkable statement. That's what he said. The meeting was adjourned. The cabinet rushed out. They couldn't wait to get out of the room, but he didn't. He stayed on for quite some time. It was like he didn't have anything else to do the rest of the afternoon. But it was a great photo op. But I was just racking my brain. What can I possibly say to our top administrator in this country, a civilian? As a scientist, what can I say that will communicate? So I mentioned the Sierra Nevadas and his ranch in the Sierras, and I tried everything I could think of. But this was September. In January, the Director of Office of Management and Budget made the announcement publicly, we're not going to deal with acid rain. It costs too much to do so, and so we're going to study it instead. President Carter had started a program called National Acid Precipitation Assessment Program, NAPAP. So the Reagan administration decided they would continue NAPAP for a 10-year period, and that the idea was that at the end of the 10 years, we would know all the scientific answers we would need to know to address this problem and to resolve it. In 1987, the first interim report was released, the first significant one of these. This is it. And the second director of NAPAP, his name was Lawrence Cole, was a scientist, but the scientists around the country that were working in the air pollution area, including me, were greatly dismayed at what was in this report. The fact that much of the science had been presented in what we thought a very biased way, and the executive summary, the booklet on the top, was particularly that way. Many of us were very upset and concerned. Much of my life has been governed by serendipity. I define serendipity as keeping your eyes, ears, and mind open, and when something interesting comes along, you jump at it. Well, out of the blue, I was invited to debate Larry Cole on TV. I thought, I don't really want to do that, but I finally decided to. And then I found out that it was going to be live, and the program was going to be called Battle Lines. So he was going to be in the studio in LA, and I was in the studio in Manhattan. Well, I became more and more concerned and worried about what I had gotten myself into. I hadn't done anything like this ever. So I happened to go to a meeting, and I was sharing my worry with others at the meeting, and somebody happened to say to me, oh, well, we have a person here who's a professional in advising when you go on television. Would you like to spend an hour with me? Yes, I sure would, right now. So we did. And he gave me 3 hints. And he said, for one, he said, TV is judged by 85% on how you look, 10% on how you sound, and 5% on what you say. So we said, first of all, you got to wear your power suit, you got to wear your dark suit with blue shirt and definitely a tie. He said, you're probably going to be in a room with a monitor, and he said the monitor is going to be somewhere to the side of you, and what you do not want to do is look at the monitor and then look back because you look really shifty-eyed if you do that. If you forget and you look at the monitor, then turn your whole head back and then it'll be okay. He said the most important thing is if the person you're debating says something you don't like, don't shout and carry on. Now, of course, modern TV is like that. You don't shout and carry on. You just shake your head like this. Because the camera will focus on motion. And so there'll be the sound going on over there with this other person, and you'll be going like this, and you get your message across. Well, as it turned out, and I have a copy of the tape, so I can prove what I'm going to say, he lied 3 times. Egregious lies, in my opinion. And so I was going and actually, I don't know what anybody else saw, but I thought it worked really well because there was this sound over here and all you could see was the Office of Technology Assessment, which is a bipartisan group you're well familiar with, had come out with this statement, quote, acid rain, ozone, and fine particles such as airborne sulfate are endangering U.S. resources. These air pollutants have harmed lakes and streams, lowered crop yields, damaged man-made materials, decreased visibility, and may be threatening forests and even human health. So a very comprehensive, strong statement about the fact that acid rain is causing significant damage. That was a big controversy, whether it was causing any damage or not. Well, the media played a big part in what was going on during this period. There were many front page stories. Here's one from the Boston Globe, July 14, 1988, and it shows a picture of this young scientist and says, Tony Bluen of Dalhousie University in Halifax, Nova Scotia, demonstrates the Van Dorn sampler, which we use, which collects lake algae that are later analyzed for levels of acidity. I don't even know how you do that. And nobody would do that. The point is, it's a great picture on the front page, but has no relevance to the story at all, and the caption is totally silly. Another one, New York Times. This one is also July 1988. Front page. Deadly combination felling trees in the east. Now the next picture is going to be of this horrible looking dead forest here on the lower left. And it says, dead trees on Mount Mitchell, North Carolina, which was covered with red spruce 5 years ago. No, it wasn't covered with red spruce. It wasn't killed by acid rain. This was a problem. But a picture is worth 1,000 words. That's a scary picture. All those dead trees. Not true, but it's a really scary picture. The National Academy of Sciences, which is usually a very conservative, particularly then laid back group, we still are, issued a white paper, and I wasn't involved in generating this. And this was for the first Bush the Senior transition team. And there's 4 things that they wanted the transition team to think about. I'll call your attention to the last one. Global environmental change, develop national policies to reduce acid rain. When I saw that, I was shocked because I hadn't expected the Academy, even though they'd had several commissions and several reports, I hadn't expected them to do that. When Bush the Senior came into office, the first thing he issued publicly was, we are going to resolve this acid rain problem. His Secretary of State, first thing he said, we're going to resolve this acid rain problem. The new administrator for EPA said the same thing. It was on their agenda. They wanted to get it done with and off their agenda. So President Bush signed new amendments, Clean Air Act amendments, 1990, into law on the 15th of November. The House and the Senate had both overwhelmingly passed legislation leading to these amendments prior to the time President Bush signed it. But as it came right down to the point where President Bush was going to sign it, he seemed to be getting cold feet. And it's my opinion that it was an emissions trading plan, this cap and trade idea, brought forth by the Environmental Defense Fund to him that convinced him that he could do it and then resolve the economic issues at the same time. That was, I think, the idea. Were there any scientists invited to the signing? I don't know, Ben. No. There were 2 EDF people there. So that's why I think it occurred in that way. NAPAP, you remember NAPAP? Well, it's boiling along all this time, a 10-year program. It was supposed to inform the policy. Well, the NAPAP report never appeared until the following early winter, January, February. So Bush had signed the amendments into law in November, and NAPAP's report wasn't issued until the following February. Michael Rodenmeyer, House staff member, I happened to hear him say, NAPAP politically irrelevant, science got tarnished in the process. NPR reporter, I was shaving when I heard this one. Quote, there is a general consensus among the scientific community that acid rain is a complicated issue, unquote. I almost cut my throat when I was shaving on that one. I thought, good grief, after all this and all this money and all this science, is that all we have convinced the media that we know about acid rain, that it's a complicated issue? You see, I've been playing with cartoons on several of these, and this umbrella is like one I got once when I was introduced during the acid rain wars. Somebody introduced me. They said, "Here, Gene, we can use this, and it must be the way your umbrella looks anyway." Couldn't ever throw it away. The third director of NAPAC, James Mahoney, said this: acid rain does cause damage, but the amount of damage is less than we once thought. Well, who's we? And what did we once think? And what's less than? I mean, just gibberish kind of information that was coming out to guide us in the policy-making process. In my view, and this is my view living through this, NAPAC acted as though acid rain research began in 1980, and that's ignoring this 10-year period of the 80s, what I call the acid rain wars. And probably maybe even after 87, they didn't make scholarly use of the massive information that was available in Scandinavia, particularly Sweden and Norway. Didn't make use of it much at all. And they spent $570 million in this 10-year effort. They did produce a lot of information, a lot of reports. They never officially did the second A, NAPAP, National Precipitation Assessment Program. Assessment, they never did an official assessment. And it is my opinion that the 1990 amendments to the Clean Air Act were passed on the information available to the public and to politicians by 1980, which is too bad. Now I want to take you to my study that we started in 1963. Beautiful area of the White Mountains, impacted by acid rain for a long time. We have to collect samples of precipitation. This is a collector that we developed. It's a simple funnel and tubing and a reservoir. We leave it out and it collects samples of rain when it falls. It took us 2 years to develop this collector. And you've got to be thinking, 2 years, they must be pretty stupid if it took them 2 years to develop a simple funnel and a reservoir. Well, the problem is birds love to sit on perches like this, and they almost always sit facing outward. And that contaminates their samples and is not good for what we're trying to do. The key to this whole process is this loop. So when it rains, water runs down through the loop and into this reservoir, but the loop stays half full. The fact that it stays half full keeps it from evaporating, keeps the sample from evaporating, because if it were to evaporate, that would seriously destroy our sample. And we put a vapor barrier on the other side, and it works beautifully. But it did take us 2 years to do it. We have more complicated, sophisticated devices, such as this one. This is a so-called wet-dry collector. Here's a sensor. So if a raindrop or a snowflake falls on that sensor, which is electrically heated, this lid moves over and covers over that bucket, and precipitation falls into this side, the so-called wet side. This is heated. Eventually, when it stops raining or snowing, it dries off. The circuit is open, and the lid goes back over to that side. So we use a variety of ways to collect our samples. Excuse me. So, so this is the long-term record for hydrogen ion, or pH, and precipitations from the beginning. Each circle is an annual value, a yearly value. So for the first several years, it was very acid, but no real trend. And then, if you look at those 3 years, it shot up like a rocket. And if you were an environmentalist at that point in time, you're probably saying, we really have to do something about this problem. The whole world's going to dissolve in an acid raindrop. But if you saw this part of the record only, you'd say just the opposite. No problem, it's all going to go away, don't worry. Neither one clearly are what is going on. It took us 18 years in order to fit a line to all of those data to answer the simple question and to make the statement, the rain is getting less acid. 18 years before we could say that statistically. As a lesson there. These values are anywhere from 10 to 100 times more acid than we would have expected if the atmosphere were not polluted. We're still 2 to 5 times more acid than it should be, but we're making good progress. We'll come back to that. NABAP concluded that forest soils in the U.S. had not been impacted. In fact, one of the scientists at Brook had suggested that the acidity was actually good. The sulfur and the nitrogen were actually fertilizers, and we should be thankful for it. This came from very recently, 1996, that the trees seem to be growing rapidly. The forest is probably in better shape than it's been in the last century. Well, when acid rain falls on the forest, part of it falls on the canopy, part of it falls on the soils. So these are the acids, sulfuric and nitric acid, and they exchange with calcium, magnesium, basic components of the soil, and aluminum. Aluminum in dissolved form is very toxic. But the calcium and magnesium, these are kind of the tongues and rollings of the system. They're the neutralizing capacity. And then these are flushed out in stream water. Acid rain affects conifers and deciduous trees differently. Red spruce, this has been worked out by scientists at the University of Vermont, where the calcium is leached from the needles, the membranes and the needles by the acid rain, and then the trees are much less cold hardy. They don't survive cold very well. Something like a sugar maple, it's a different situation where the calcium and magnesium and then the aluminum in the soil is affecting the roots primarily. So it's the leaching of calcium and magnesium and mobilization of aluminum that is affecting a tree like sugar maple. What we found in one of our watersheds that's been studied for a very long time, starting in 1965, it's a whole system evaluation. Every tree is measured and analyzed now every 5 years. So in 1965, this is the amount of biomass in that forest, and it was recovering from cutting in about 1917 or so. And it was increasing in 1977, 1982. Our models had suggested it was going to increase. That didn't happen. Either our models were wrong or the air pollution affected it. But it was relatively flat, being done every 5 years. And then it started to bend over, to decline. The amount of biomass in the system declined. And then the last one we've done, 2007, the decline was actually statistically significant, more than 10%. So the system is starting to fall apart primarily because of death of trees. Death of trees, increased mortality shown here, which mimics the decline there. What's it due to? Well, we've wondered this for a long time. Is it natural? Is it because of changing climate? Is it because of the fact that our models were wrong or inadequate? Is it due to the air pollution that I've been talking about? The lowest pH we've ever measured at Hubbard Brook was 2.85. That's really acid. Really acid. Necrotic spots all over the leaves after that rain event. Or ozone. We have ozone outbreaks, even though we're quite some distance from major metropolitan areas. Disease. We've had a major outbreak of leech bark disease. Cary Institute is here, has done a lot of work studying forest diseases. So that's impacted the forest. Or is it nutrient limitation? The paradigm is that nitrogen is a prevailing important nutrient for forest growth, for these kinds of forests. But we have leached so much calcium and magnesium out of the forest, could that be a factor? In fact, we calculated how much calcium has been leached by acid rain in this period 1940 to 1995, published here. It was a lot. More than 50% of the available calcium in the soils were leached by acid rain during that period. So, in the sort of classical Hubbard Brook ecosystem approach, we did a whole watershed experiment. We had a mineral called wollastonite, calcium silicate, mined in the Adirondacks. It was then ground to a fine particle and pelletized so that we could handle it. And then we added back a little bit more than we calculated had been leached by acid rain. We added it all back by helicopter addition, GPS-guided helicopter sprinkling this wollastonite all over an entire watershed. This is the way the particles look on the forest floor after that happened. That was done in 1999. The effect was immediate. The pH increased because calcium silicate is a base, so it increased the pH. The calcium went up, the silicon went up. Actually, some of the pellets fell directly in the stream, so we would expect that, but it's still higher than it was previously. But very significantly is we're seeing a biotic response, and I'm only briefly mentioning that. These are seedlings of sugar maple within the treated area. These are seedlings, a seedling, not in the treated area, in a reference area. You can see these are bigger. We know that there are more of them, and maybe the greener, and maybe they're even tastier. Red spruce, this is the way red spruce looks with winter injury because of the calcium that's leached from the needles, and then the cold causes the tree to could even be killed by this effect. And in the wollastonite treated compared to the reference treated, there's a very significant protection by adding this calcium silicate to the system. It's a percent of winter injury much less than where it was not added. So that suggests that calcium is a very important plant nutrient that we didn't know as much about before in affecting the forest at a place like Hubbard Brook. Then there are these kinds of articles that come out. Scientific American, 2010. Acid rain is now caused by nitric rather than sulfuric. No, it's been caused by nitric and sulfuric acid from the very beginning. I don't know where these articles come from, but they're very misleading to the public because it means, okay, we don't have to do this in terms of policy, we only have to do that in terms of policy, and that's just not correct. One of the true things is it takes a long time. There's a need for basic answers. We had to go to several of the most remote places in the world to find out what the background pH might be. We went to an island in the middle of the Pacific Ocean called Amsterdam Island. It takes a month by ship to get there. There's no landing strip on the island. We went to southern Chile. We went to a remote place in Australia, and so forth, to try to get answers about what the pH was like before man began to pollute the atmosphere. It took 3 presidents and 1 pope in 27 years to come up with the 1990 Clean Air Act amendments. So here's Reagan, here's Carter, Bush, and Pope John Paul II. We had a week-long meeting in the Vatican. At the end of that meeting, Pope John Paul issued an encyclical. He accepted our report. Probably that encyclical had more impact on world opinion on these kinds of pollutants than any science I did. I hesitate saying that, but I think that's probably true. With the effect on forests, it's arguably fair to say that the problem is no worse than we thought it was in 1970 or 80 or 90. Because even though the amount of acidity is decreasing and is now much less than it was in the atmosphere, than it was in 1970, 80, or 90, the system that it's falling on, the sensitive system that it's falling on, has lost its tums and rolades. So it is much more sensitive to the amount of acidity that's still falling. So the impact is arguably worse than it was before. The 1990 amendments to the Clean Air Act were the first federal legislation focused on acid rain. Hubbard Brook did have a very important contribution, particularly because of the long-term data. Time to tell you at least one more story. I had a contract put out on me, not for my life, but for my career. The contract was offered to test what we knew about the data at Hubbard Brook and what I had been saying. It was worded this way, the call for proposals. Likens has said 1, 2, 3, 4, 5, 6 things I have said in publications. The call for proposal was, show that he's wrong. They issued that contract for $400,000 to a consulting firm in California. And I think one of the things that I'm most proud about in my entire career is that they weren't able to do that. They tried really hard. It took 5 years to implement the 1990 Clean Air Act. So we have these emissions occurring in the Midwestern United States, primarily, not exclusively. We have emissions in New York State here, of course, but most of them are in the Midwestern United States. And they're working their way through the atmosphere a very long distance, thousands of kilometers, to us and to New Hampshire and Maine, and then coming back down. Those pollutants have a very strong correlation with what we measure in our little funnel or in our streams at Hubbard Brook. When the amount that is emitted is high, here, the amount that we see in our precipitation is high, and our streams is high. And the relation is very, very strong for stuff that has just mixed in the atmosphere and gone a very long distance. To calculate it, I love this calculation. Less than 0.001% of the sulfur that is emitted in the source area, the area that directly the state's emissions that directly impact Hubbard Brook. That tiny amount during that period has this impact on our system. If that doesn't convince you that we're a connected system and that what is done over there can affect you over here in a very significant way, I don't know what way. It does me. I mean, I collected these data and I'm blown away by the fact that there is that much connection in a system. You know, it doesn't rain every day, only rains sometimes, only snows sometimes. Those pollutants get all mixed in the atmosphere and they get transported all over the place, and yet we have this really strong relationship. That's what was convincing. That's what was convincing to the politicians when they looked to the science. So, air pollution leading to acid rain has caused a variety of environmental problems on aquatic systems, terrestrial, structures and monuments, particularly human health. I've not mentioned that at all. And did we get our money's worth from all this legislation and all of the science that was done? Well, the EPA did a cost-benefit analysis. This is the one they did in 2003. And they estimated the costs from the previous 10 years before 2003 were between 8 and 8 billion per year. But the benefits were 101 to 119 billion per year. So yes, we got our money's worth. we got our money's worth. We don't want to breathe dirty air, and we would like our lakes and forests to be protected from these kinds of pollutants. So communicating with the public and policymakers, Peter Cullen, who's one of my idols, he's an Australian who recently passed away, said, "Committed and knowledgeable scientists can make a contribution to public policy if they're prepared to speak out." But he also said, if you speak out, you got to know the rules, because the rules are different. In each component of our society, the rules are different. And you've got to know the rules if you're going to play that game. I said in an article in Science, and it sounds very trite, but I said, speak out when you have something to say. Actually, it's not trite. I think the Nobel syndrome, you win a Nobel Prize and then you're asked to comment on every topic in the world as an authority, that's nonsense. You speak out when you have something to say. And we often, as scientists, maintain and obtain our credibility through scientific publications. I've mentioned cartoons many times tonight and shown you several as I zip through. This one I particularly like. It says, an acid rain shower got to him before I could. Well, no. Acid rain is not nearly strong enough to dissolve away the meat on that fish. If anything, it would dissolve away the bones and leave the meat. But that doesn't happen either. It's one of those examples where a picture, a stark picture, makes a strong point. It's a little white lie, isn't it? It's not true, but it makes a point. Are those little white lies when they're on our side? Okay. But not if they're on the other side? Okay. So I think cartoons, in my view, in this whole issue of acid rain, have had a huge, huge impact. Kept track of the number of times acid rain or acid precipitation appeared in the New York Times. So here's that. Here's that first article that I started with about my work at Hubbard Brook, and then not much. And then here's the acid rain wars, hundreds of times a year. And then we passed the 1990 Clean Air Act amendments. Problem's done, big sigh of relief, no longer any problem, and the attention drops way off, and we've been going along something like that ever since. So where do we go from here to resolve this problem? Because it's not resolved. As I said, arguably it's worse than it may have been in the past. So it remains an important problem. It's an emerging issue in China. China is on a time bomb of some sort because they've still got all these particles in the atmosphere which are neutralizing the acid rain. That's why they wear the mask, because of the particles. They remove the particles, which they have to do from a health point of view. Acid rain is probably going to come on gangbusters. The increased importance of nitric acid, aluminum, calcium, magnesium, forest ecosystems in sensitive areas like I've shown in our area at Hubbard Brook are now much more susceptible to continuing inputs, even though those inputs are smaller because they've lost their buffering capacity. The 1990 Clean Air Act amendments focused on sulfur. Nitrogen was mentioned, but the focus was on sulfur. It's not going to be adequate to protect sensitive terrestrial and aquatic ecosystems unless we do something with nitrogen. Nitrogen is now starting to decrease in terms of emissions, and we need to do that more. It's going to take a very long time. It has taken a long time, but it's going to take an even longer time. So when these issues arise, it points to the need for some action before they build up such a legacy that the time is even longer. Some of my thoughts about what's needed to meet those challenges, I think we have to listen to one another. We have to stop lecturing to one another. We have to listen. If our results, our science is going to be relevant to management and to policy, We have to listen to one another. And we have to use some of the research that results from listening to one another. We need to speak out as scientists on issues when we have something to say, based on our expertise. And for that, we need scientific credibility. How many of you have read Merchants of Doubt? We all need to read Merchants of Doubt. It's a very shocking book. It's so easy to spread doubt. And Merchants of Doubt, I don't get any commission from it. Merchants of Doubt starts with a discussion of tobacco and smoking, and goes through acid rain. I'm actually in the book, that's why I should read. No, I'm kidding. It goes through acid rain, goes through DDT, ends with climate change. It's a book that you really need to read. We need to devote as scientists significant amounts of time, because it takes time, in addressing these issues. So we have to be patient, we have to be persistent, and we have to do the very best that we can to make our data the highest quality it can be and the most effective that it can be in resolving these problems that are literally eating away at our life support systems of clean air, clean water, clean soil, clean food. Thank you very much.
Questions of the audience before we recess to a reception in the Plant Science Building. So let's have a few comments and questions from people. Yes, right there.
Several parts of the world that real specific are starting trying to find out areas where perhaps untouched by industrial pollution. Where did you find out?
The question was, from these studies we did in the remote areas, what were the background values that we found? We came up with pH of 5.1 as the background value, and it's very hard to get that answer. There are many things that affect the pH, like volcanic eruptions. And for a while during this debate, there were arguments that, oh no, there's no human input here at all, it's all volcanoes. And so that's why I made the point about the submarine copper-nickel smelter emissions. So we had to go to really remote areas. And 5.1 is the number that we came up with. I would think that number has an error limit of maybe 50%. Because 5.1 has a hydrogen concentration of, what is that? It's about 9, whatever it is. And so somewhere between 4 and 12. But that's the best we can do. Obviously, sitting right here in front of the 9 and working on background values are very hard to come by. I just published a paper 2 weeks ago from Hubbard, Brook, which shows that our chemistry is just dramatically diluted, both precipitation and stream water, dramatically diluted, which actually makes it much more sensitive as well. And so we've been trying to predict where baselines for that might be. And they're very low. And we have argued in this paper that they're going to be affected by the acid rain that has been falling on the system now for about 60 years. We suggested that acid rain started as a phenomenon. I mean, there's been emissions for a very, very long time, volcanoes and all this source, but as a phenomenon in the mid-50s, early to mid-50s. That's when it seems like the buffering capacity of the atmosphere got overwhelmed and we began to see real acid rain falling. I'll try to cut my answer short.
You mentioned the necessity of the scientists listening to each other.
Yes.
In your opinion, is there great consensus? Is there good cooperation in the scientific community that could actually then be a force to make it a little more poignant and speakable to do something against the falsification in the media? I mean, scientific journal, you think you get the right stuff, right? So.
Well, I'll try to answer that question in a couple different ways, really. This one isn't going to be really short. But what happened in the acid rain issue is not like at all what is happening currently in the climate change issue. And as scientists, we're trained to be critical. So if you develop something and publish it, I'm going to try to find out if it's okay, if it's wrong, if it's right. That's what we do. We search for the truth. We don't ever find the truth, but we search for the truth. And so clearly we're going to disagree on issues. In the acid rain wars, the vast majority of the scientists that were working in the problem knew that it was a problem, had measured it, and were trying to find solutions. But there were some that were not. I could tell you stories all day. I'll tell you one at this point. When I was here at the Institute, I was invited by a very kindly man on the board of the New York Botanical Garden to meet with him and two executives from the second largest coal company in the U.S. and one of the clubs in Manhattan, the lead club. And I said, I really don't want to do that. I said, well, I think it would be a good idea if we maybe resolve your differences. And I said, no, I don't think we could, but I really don't want to do that. But he was a very nice man, and I finally did. Jim Hester, president of the garden, also attended that lunch. So I witnessed this morning, I will tell you. At lunch, these two executives said to me, quote, there's several quotes I will never forget. We, our company, have hired a whole room full of PhDs to obfuscate, confuse, and delay at every opportunity the acid rain issue unquote. Obfuscate, confuse, and delay? I said, one thing I can think of, how big was the room? And then I sort of got my senses and I said, how do you sleep at night? How in the world do you sleep at night? And they said, well, we don't sleep very well, but we sell coal to the electric utilities and they play hardball with us. And unless we adopt that line, they don't buy our coal. Obfuscate, confuse, delay. So there's that dimension in the answer to your question as well. Honest disagreement, honest search for the truth, and then there is clearly some other components. I've always been rather naive, I suppose. But that shocked me to the core.
Perhaps one more?
My granddaughter.
The acid rain gets like into the stream under water, in the water. They put cathode in it. They also clean. There's clean the acid.
Cattails, you say cattails?
Yeah.
That's probably the toughest question I'm going to get. The question was, the acid rain gets into the stream or lake, and if there's cattails there, will the cattails clean the water and reduce the acidity, right? That's the question. The answer generally is yes, but it doesn't work very efficiently, and cattails aren't in every stream by any means. The kinds of streams that I work in, and you know this from visiting us, kinds of streams I work in and the lakes I work in don't have cattails. Cattails are a plant that are more or less dependent upon high calcium, magnesium, rich soils to grow. And so the kinds of systems we have don't even have cattails. But yes, as I said at the very beginning, it is an ecosystem issue. And so there are all these components that are working together. We have to really try to understand how they all interact and work together to find a solution.
Gene, many thanks for a fascinating story. It may have been a frustrating time for you, but I think all of us in the room and the future generations are going to be really glad that that battle was fought and hopefully won, and the world will be a better place for you having done so. Many thanks, and now I welcome all of you to join us over in the Plant Science Building for a little libation and a chance to chat and celebrate all that Gene has done here for so many years.
Correction and all that.